Okay.
Okay, good afternoon, everyone. Welcome everybody to this 82 session of our seminar. Today we have a pleasure to hear two great mathematicians. So first speaker will be Susanna Terracini from the University of Torino, Italy, who will be presented by Luz de Teresa. And the second speaker will be Sara Stricuerda from the University of Pennsylvania from the United States. So please, Lucero, you can start.
Yes, thank you, Anna. So it's a pleasure to present Susanna Terracini. So she got her PhD degree at Sessão in Italy, and she's an expert on chaos in Hamiltonian dynamical systems, including the n-body problem, reaction diffusion systems, and Schrödinger equations. She was winner in 2002 of the Vinti Prize of the Italian Mathematical Union for Young Researchers in Mathematical Analysis, and in 2020, she received the Schauder Medal from the Nicholas Copernicus University in Toruń, Poland. And as Anna said before, she will talk about boundary Harnack principles and degenerate equations on singular sets. So welcome, Susanna.
Thank you, Luz, and thanks to all the organizers. I'm very happy to be here tonight and to share some results and some problems and some thoughts with you. So the subject of the talk are the boundary Harnack principles and the degenerate equation on singular set, and I'm going to report about papers and results that I have obtained in collaboration with Yannick Sire, Giorgio Tortone, and Stefano Vita. And here are the papers. We have actually two published papers by a set of authors, Sire, Terracini, and Vita, and two papers, one submitted and one which is going to appear on the archive in a very few days. Okay, so what are the Harnack boundary principles? Well, everyone probably in this audience knows what is a harmonic function, okay? Harmonic functions are basic objects in mathematics, in analysis, probability, mathematical physics, and so on. And among simple harmonic functions, we have harmonic polynomials. Well, first, all linear functions or affine functions are harmonic, and then we have a number of second-order harmonic polynomials. And in general, for every given degree, we have harmonic polynomials, a class of harmonic polynomials of degree n, which are in fact related with the spherical harmonics, so the vibration modes of a sphere. And then they are also important, the harmonic function on cones, which in polar coordinates have this form, the one in 2 dimensions, so they are of this type, and they satisfy Dirichlet boundary condition on the cone. And as you see, because alpha can be smaller than 1, can be Hölder continuous, but not C1 or more smoother than that. Well, harmonic functions enjoy the mean value properties, are analytic, and so on. And let me state a well-known result. I restate a very classical Liouville theorem as follows. If you take an entire harmonic function which grows less than linearly at infinity, so strictly less than linearly, is necessarily constant. And in fact, one can play with this theorem, for example, to prove regularity of and up to C infinity for this solution. Okay, what is the classical boundary Harnack principle by Jefferson and Cuding on a seminal paper in 1982, and say, okay, for smooth boundaries, but even rather rough boundaries, which enjoy a special properties, they are called to be non-tangentially accessible, NTA, the ratio of two positive harmonic functions that vanish both on the same portion of the boundary of the domain is Hölder continuous. And this is locally Hölder continuous. So the ratio of the two, be careful, because it's already a gift that each boundary, the denominator must have a sign, it must be positive in omegas, otherwise it's not true. So the denominator u is a positive function in omega, but v and u both vanish. And when you have two Hölder functions, the ratio is not an Hölder function. Okay, this should be clear. Basically, when you divide by vanishing u, you are losing morally one degree of regularity. So this is absolutely non-granted. And then if you know that the boundary is ck alpha, so if you raise the smoothness of the boundary, then you have we have at our disposal higher order boundary Harnack principle that say that the ratio, under the same assumption, the ratio of two harmonic function stays in the same class, ck plus alpha. Okay, and this is a principle which is very well known in the world of free boundaries, because says that even if you know very little about the regularity of the boundary, because probably because it is an unknown itself, when you have two harmonic functions, maybe having the same sign, that vanish on that boundary, they behave more or less the same. This can be also be seen as a division lemma. Okay, v can be or u divides v. Okay, what are NTA? I will not explain in details. There are basically three conditions. The first is the so-called corkscrew condition, which is written here, that when you take a point in the boundary, then there is another point inside which somehow realizes up to some constant, the distance from x, and then both omega and its complement satisfy the corkscrew condition. And then there is this very strange assumption that say that somehow you can control for every pair of points, you can control the length of a path that joins the 2 points with the distance of the 2 points from the boundary. And okay, so this is not the subject of this talk, but the theorem, the celebrated theorem by Jefferson and Cuddy, say that when you have an NTA domain in a neighborhood of a point and two boundary conditions and two harmonic functions, with one which is positive, but they both vanish on the same portion of the boundary, then the ratio v over u is Hölder continuous of some order that depends on this constant. Sorry, of this constant appearing here in this definition, the constant m, and such that the ratio is Hölder continuous. In particular, you have well defined the ratio of the two also on the boundary. Sorry, this should be a boundary. There is a partial sign missing here. And so V of x is some multiple of ux for a Hölder continuous function omega. Okay, now all Lipschitz boundaries are NTA. And so, for example, we know that solutions of harmonic functions on cones may not be C1 and may not even be harmonic. It depends on the opening of the cones. And here we have a drawing that more or less explains this strange property that somehow the length must be controlled in some particular way with the distance to the boundary. Okay, this is the starting point of the talk. More recently, these principles have started being extended to boundary Harnack principle on nodal domains. So this, what I mean, I take the elliptic operator, a plain elliptic operator on a domain, for example, in the ball, and then I take two solutions, U and V, and suppose to know that V vanishes whenever U does. Okay. And we assume that the zero set of U lies in the interior of V1, at least a piece of it lies in the interior of V1. And then we seek a comparison principle between U and V, which can be expressed in terms of Hölder continuity for the ratio, and maybe possibly for the derivatives. Okay, so in 2015 and 2016, Logunov and Malinnikova published two papers where they proved that the analyticity of the quotient V over U when the operator is a Laplacian, but the same proof works for operators with real analytic coefficients. Okay, and the proof here is based on a division lemma that this year is celebrating its 60th anniversary by Murdoch. Let's say the following. You take two polynomials, Q and P, and Q is harmonic, P is or whatever, and assume that the zero set of Q is included in the zero set of P. Then Q divides P. Okay. Okay, this is a non-trivial fact because in general, as well known, the quotient of two polynomials is not a polynomial, not even when the two polynomials share the same zero set. Okay, this is not true. One can really find immediately a lot of counterexamples. Okay, this is an interesting lemma, which is somehow something that raised in the context of algebraic geometry. Okay, now if you take an elliptic operator or whatever, yeah, a second order operator actually in divergence form, and you take the ratio W of the V over U, then in fact the ratio satisfies an equation, an elliptic equation, where the same matrix, the same metric A is multiplied by a weight, which is the square of the denominator. Okay, so this is a degenerate equation, an equation which is elliptic but degenerates on the zero set of U. Okay, and okay, so this is even in the simplest case, for example, where A is the identity and U is a linear function, this is an equation which is very, very degenerate at the characteristic hyperplane. In this case, the characteristic hyperplane is just the zero set of U. And several authors remarked this fact, and this fact, in fact, has been used. For example, it's very often used when you want to prove the validity of the maximum principle. I remember Nirenberg was very fond of this weighted equation. But to get regularity, it's very much, it's too much degenerate and was discarded and not used in the literature. For example, it basically does never belong to the class of good ways, which is called the Mukhenaupt class, for which solutions are known to be Hölder continuous. Okay, well, now we are going to try to attack the problem of the regularity of the quotient through the study of this incredibly, amazingly degenerate equation. Okay, and now we start with the simplest case, which is not satisfactory, but we will start with when the zero set is actually a very irregular hypersurface gamma. Okay, and now we consider two cases. The case when gamma is contained in the boundary of our domain omega, or lies inside omega. Okay, in the first case, when it is a part of the boundary, then we use the notation omega plus to emphasize that actually omega lies on one side of this hypersurface, this characteristic hypersurface gamma. Okay, and also we consider a power here that could be even different from 2 and even negative, provided is larger than -1. Okay, so this is to depict the two possible situations. Okay, and what do we mean by a solution? Well, we take the weighted Sobolev spaces, the Sobolev space with weight rho to the A, and we consider a solution in the sense that is a critical point of the Dirichlet energy associated, which is well defined on this weighted Beppo-Levi space for suitable data small f and capital F. Okay, and then we find such solutions. Okay, I'm a bit sorry, I'm a bit lost. Okay, and this type of problem also arises in the study in the context of fractional powers of elliptic operators. This is the particular case when the exponent A is between -1 and 1 in the analysis of edge operators, and which they appear in the study of geometric PDEs in very context. For example, when you have a metric, a manifold with a boundary, a metric which degenerates as a metric on the boundary, so somehow particles cannot reach the boundary, or if you like, yeah, the metric degenerates on the boundary. Okay, be careful, because we have in fact a different type of degeneracy. When A is between -1 and 1, we are in the case of Mukhenaupt weights, and in that case, elements of the Sobolev space do have a trace on gamma. Otherwise, they if A is larger or equal than 1, the space, sorry, this is omega minus gamma, the set of functions that vanish on gamma, okay, in a neighborhood of gamma, is dense in the energy space, so traces are meaningless. In any case, take care, be careful, because our definition of solution incorporates a boundary condition, which is a natural boundary condition in the sense of Neumann, okay? But also when A is negative, this is not very much meaningful, because this weight is when A is positive, this weight is in any case annihilating at the boundary, so this is not very, does not give very many information, okay? So we are in fact associating with the equation the natural boundary condition omega, okay? When A is larger or equal than 1, because of the density of function that vanish, annihilate on boundary of gamma, actually all energy solution of the equations in the are all distributional solution of this equation that belong to the energy space are solution in our sense, okay? But again, notice that when A is larger than 1 and gamma fall inside the boundary omega, energy solution can very well be discontinuous. Okay, now we consider the more simple case of gamma, which gamma is not a hyperplane, it's just a flat, gamma is just an hyperplane. In this case, we call y the coordinate that gives the distance to the characteristic hyperplane, and x an element of Rn, so that the dimension is now n+1. Here there is a little jump in notational jump. Okay, A is an symmetric, continuous, and uniformly elliptic matrix. Okay, and now let me just remind the very well-known theorem, basic theorem for elliptic regularity of the homogeneous problem, when we have a symmetric matrix and which do not need to be continuous, but in any case uniformly elliptic, and you take a solution of the divergent of the operator in divergent form, then solutions are in the Hölder space for some alpha that depends on the parameters of ellipticity. This is a local in omega result, and when A is continuous, we can take any alpha between 0 and 1. Okay, now I restate also the same theorem in the case where there is a right-hand side. In this case, we have if f is small f and capital F are sufficiently integrable, then we have the solution again is in a space of Hölder continuous space, and we have these estimates. And if we want to go a little bit further on in the regularity theorem, in the interior regularity theorem, we may recall the Schauder estimates in a form that is due to Campanato and Giaquinti and Giusti. When A is has Hölder continuous entries, the solutions are C1 alpha under natural assumption on small f that must be integrable with a sufficiently high power that depends on the dimension, and the capital F, the vector field F, is C0 alpha itself. Okay, now generally speaking, we cannot hope that solutions are very smooth if we don't associate the right boundary condition. For example, if we take the weighted Laplacian and we take this type of solution, and A is between -1 and 1, this is a solution and lacks smoothness in general. Maybe at most may have at most some Mulder continuity, and well, of course, A can be positive or negative. When A is not an integer, in any case, will lack smoothness. Okay. Now, let us recall what a Mückenhaut weight is. We need that the averages, the integral averages of rho and of rho, the rho to some negative power are, so the product of the two average is finite over all possible balls. And this type of weight belongs to the class AP when A is between -1 and P-1. So if we wish to reach the class A2, which is the safe class of the theory of weighted operator in divergence form by Fades, Koenig, and Serapioni, we need the power A to be between -1 and 1. In this case, there are nice embedding properties of the energy space. In particular, we have weighted Sobolev embeddings and Poincaré, weighted Poincaré inequalities, which entail the validity of the maximum principle, unique continuation principle, Harnack inequality, and eventually Euler continuity of all energy solution. Okay, but now we want to treat the case of super degenerate weight, but also to look at those solutions which satisfy the Neumann boundary condition. Okay, and again we see that in this case, if we take a ball, the full ball, and we take the jump function between -1 and 1, this is a solution. Okay, but of course it's not continuous, so things become a little bit tricky. So at first we stay on one side of the hyperplane and we regularize the weight in a way that becomes C infinity, even analytic, in this way. Okay. And we also regularize the right-hand side, and now our point of our angle in the theory is to derive C0 alpha and C1 alpha estimate, which are uniform with respect to the parameter epsilon that appears in these regularized problems. Okay, and this is in fact what we have done in the papers in the joint paper with Sire and Vita. And okay, so n+1 plus A plus is the homogeneous, n+1 is the full dimension, because we said y has one dimension, xy has n dimensions, so n+1 is the dimension. Then we also have to add the positive part of the exponent A, and then we find exactly the same Schauder estimates up to the boundary, okay, up to the boundary that we had for the interior case, okay. And we have an estimate for the whole class of problem, which is epsilon stable in the sense that applies to the whole class of regularized systems for any positive epsilon, including epsilon equal to 0. Now, this is important because it has another important consequence, because we have C1 alpha estimates, and now when we look at the regularized problem, you see the Neumann boundary condition is a plain one, because this weight, when y equal to when y is equal to 0, is not 0, so just cancel. And we have the usual Neumann boundary condition. So this Neumann boundary condition propagates into the weighted problems. Okay, and okay, so we see that the joint effect of the boundary condition, of the natural boundary condition, and the ellipticity, let's say, creates this little miracle of bringing the Schauder estimates up to the boundary, to extending up to the boundary. And if we are interested in higher order Schauder estimates, then of course we must assume that the data, the entries have the right class of regularity, and then we find again that the solution belongs to CK plus 1, so gains 1 with respect to the entries A of the metric and the vector field F, and gains 2 degrees of regularity with respect to A. Notice that this is a bit a strange result, because in this case the data, okay, and the data, so the complex of the y to the A times the entries of the matrix, and also here are basically have less regularity than the solution, because when A is not an integer, and you know the regularity depends only on the regularity of A, and small f, and there is no role of the exponent A. Okay, and then we find this estimate on the CK plus 1 alpha, which depends, of course, is bounded linearly by the data. What we have done is we have avoided this type of solution by imposing the boundary condition that excludes this type of solution. Okay, we also have, and this is important, we have also a result, okay, when the exponent in front of the datum, the forcing f, is A minus 1. So this is basically a singular problem. In that case, when A is positive, we find again all the results of the previous theorem, okay? And moreover, what it changes a little bit is the boundary condition, where also F appears. Okay, this may be important in some later. Okay, so as I said, the scheme of the proof is to regularize, to somehow argue by contradiction, saying, okay, we assume that this uniform in epsilon estimates are violated, and then we all blow up. We end up with some entire solutions enjoying some boundary value problem, and we prove that these are not that there was some Liouville type theorem that I think may be of some interest. In general, we also have to prove that the limits of the regularized problems exhaust all possible solutions. Okay, this was a first work that, of course, can be extended to the case of a hypersurface gamma, which is not flat, but is regular enough, is the graph of a function which is sufficiently regular. Okay, now let's take a fixed boundary, such an omega, and now we take two functions, f and v, that solve some elliptic equation, with maybe some right hand side. U is a positive function in the interior. The characteristic manifold lies on one side of omega lies on one side of the characteristic manifold. The two functions vanish on the same part of gamma, and we assume, moreover, this is not granted if G is not zero, that U is positive and the inner boundary, in the inner derivative is negative at the boundary, is positive at the boundary, sorry, the exterior one is negative. And then one immediately sees that the ratio is an energy solution to this degenerate equation with U, and on the right hand side we find some singular right hand side, and okay, so we have here U square and here U, but as I said, this doesn't matter too much, and we can prove that in fact the desired Harnack, even higher order Harnack principle. Okay, be careful again, because we know that both U and V are CK+1 alpha. Okay, this is the Schauder estimate up to the boundary, but the quotient of 2 CK plus alpha function, where the denominator vanish of order 1 in a non-degenerate way at the boundary, in general loses 1 of regularity. Okay, this theorem says that no, it doesn't lose anything. There is no loss of regularity. There is a nice boundary condition, and so we have this estimate. For those in the audience who are acquainted with the usual higher order Harnack principle, this is the blue part, maybe is more familiar. More familiar, of course, we have to assume that V, also the numerator is positive inside, and here is the bound we find. Okay, this is actually was previously not exactly this way, with a little in the less general case with no F and G, was proved by De Silva, Sabin, and also by Kukulian, also in the case of parabolic. Okay. Now we go to our the core of my presentation. Okay, which is now related with the fact that we assume that there is a relation with the denominator u and the characteristic manifold. Okay, so we assume that u and v, u is a weak solution, but even not a weak solution of the elliptic operator in the ball, and we take its nodal domain. Now, okay, we assume that we have another solution of the same equation, which, by the way, vanishes on the same nodal domain of u, and we take the ratio, okay? And now we would like to extend at least up to the usual Schauder theory, the regularity theorem, the regularity theory that Logunov and Mandylnikova have obtained in the framework, in the analytic framework. Okay. No. Sorry? I don't see. I cannot hear. Is there any problem?
I don't hear, also me, I don't hear just a voice there. I think maybe somebody opened the microphone.
Ah, okay. But you can hear my voice.
I hear you perfectly, Susanna.
Okay, perfect.
No problem.
Okay, now let's go at the structure of the nodal set of a solution of a some. Oh, sorry, I sometimes I get lost. Okay. Now we take this equation, and what can we say about the nodal set of a solution of this elliptic equation? Okay, where the matrix A will be a symmetric uniformly elliptic matrix with Hölder continuous coefficient. Even we can, let's think that it's Lipschitz to simplify things. Okay, then now we consider, we know that solution are C1 alpha, and the zero set has a regular part where the gradient of u doesn't vanish, and the singular part where the gradient of u vanish, and the regular part is locally n-1 dimensional hypersurface of class C1 alpha, while the singular part is small in Hausdorff dimension. Okay. Now we take a second solution, and we assume that the solution vanish wherever u does, and we take the ratio v over u. Okay. Now we in fact we seek Schauder estimates, and in fact what we can prove for the moment is the our Schauder estimate across the regular part of the nodal set. Okay, and this is somehow follows from the previous result. If we know that the data are of class CK plus alpha, then we are in a set where there are no singular points for the nodal set of U, then, I'm sorry. Okay. Then the ratio is of class CK plus 1 alpha, and the ratio satisfies Neumann boundary condition, so has zero normal derivative on the regular part. Okay. Okay, so this is a first result on which is a bit unsatisfactory because it only look at the regular part of the zero set. In later we will try to elaborate a little bit more only on the also on the singular part. Okay, what is behind this Schauder theory is a Liouville type theorem. Okay, here remember that this weight is either 1. If either square root of 1 plus y squared to the power a over 2, or y to the power a. So we consider our Neumann problem with regularized weight on a half space, and we assume we take a function w, which is an entire solution on the half plane of this. So of course, at this point, if you like, you can reflect omega on the other half plane and assume that w is an even function in y. So, well, if you assume that w grows less than linearly, then it's constant. And there is more, that this goes to get the C1 alpha, we need to have the same for the gradient. If you know that the gradient of w grows less than linear, then either w is an affine function. So sorry, if you have a solution of this type, then w is an affine function that depends only on x. X is the variable in the characteristic hyperplane. Okay. So we have this corollary, which is very important. And this type of Liouville type theorems are at the core, at the very basis of our result. Now, this division lemma by Murdoch, the one I have already mentioned before, can be restated in the form of a Liouville type theorem. And then we can say that if we have a harmonic polynomial, u, and an entire harmonic function in Rn, with a zero set which is larger than that of the harmonic polynomial, and we assume that the ratio of the two grows in an algebraic way, then the ratio is a polynomial itself. This is just a restatement of an elaboration of the Murdoch theorem. Okay, and then you can elaborate it more, and you could take a harmonic polynomial and any entire continuous solution of the weighted equation. And we assume that W, this continuous solution, continuity is not granted, grows less than linearly. Then W is a polynomial of degree at most gamma. And with this, we can, in fact, extend a similar theorem given by Fangualin and Lin, and obtain a uniform Hölder continuous bound for solution. Now we try to understand. We go to the equation, to the weight equation, and we say, okay, what can we take? What assumption can we impose on U in a way that to have good compactness properties? And a good, reasonable assumption is to take weights which are normalized in L2 and have a bounded frequency. I will not go into the detail. The Almgren frequency function is rather well known in the context of free boundaries, also in general for unique continuation, and is a quantity which is, for example, bounded for harmonic polynomials. And then we have this theorem in any dimension. If we take two pairs of solutions of the equation, which are normalized and have a bounded frequency, then the ratio of the two in C0 alpha is bounded by a constant. Okay, by a constant. Okay, now the point is, what is this constant? Does this constant depend on the particular U we have chosen, or can be taken uniform with respect to the class, to this class? Sorry, to this class, the class. Well, what is interesting is that it can be proved to be uniform with respect to the class. When we wish to go have higher order Schauder estimate means in this case that we want to go from Z0 alpha to C1 alpha, then we have to go back to the case n equal to 2, so into two-dimensional case. And in fact, we succeeded in having the right estimates. And again, the constant C depends only on the bound n0 that we have in this class. Okay, and then we can extend all the theory to all the theorem to the general class of weighted equation, where U is a harmonic function, or U and V. U solves, sorry, here there is a matrix A missing, but we can take any power of U. In this case, in fact, we could prove in a non-trivial way that Liouville theorem, which I think is maybe interesting, if we take a harmonic polynomial and an entire solution of this weighted equation on the whole of R2, and we assume that it grows less than quadratic, then it is... Sorry, they are closing the building. So this is interesting. Then U and V are both affine function, and they are conjugated. Okay, and this is interesting because a notable class of solution of this equation can be obtained this way. We take a harmonic polynomial U, and we take his harmonic conjugate, then the pair UW solves the equation for every power A. So this is a huge rigidity result about this type of equation. Okay, now my time is over, I think, because I could give some hint of how to prove this. This is basically a complex analysis lemma. Maybe have some point of interest, but maybe it's too technical. And then I thank everyone for the attention. And well, that's all.
Okay, thank you very much, Susanna, for this nice talk. Luz de Teresa had to go, so she had some issue to attend. So I'm here. So are there any questions or comments from the audience? You can use the microphone or chat.
No, I don't.
Just one question. We were talking, we coincide with Luz de Teresa with the same question, more or less. what about the evolutional problem?
Okay.
Can we extend this result to?
No. Well, I think that everything can be done, can be tried. Okay, I think there should be a theory also for the parabolic case. First, we don't have a Murdoch lemma for caloric polynomials to start with. Already a problem. Also, validity. Okay, I think that in general, this is just the beginning of a story. I hope. Okay, the story is well, we can treat. Well, the parabolic case. There is a student of mine which has, I think, already finished the paper. But extending the case of regular manifold. So the simplest is not simple, but it's not simple. I think that in general, we can think of having an equation that degenerate on stratified set. This stratified set could be the zero set of some other function. At this moment, we need that both function u and that u solves an equation, and so that it must solve an equation which is related with that of w. Maybe this is not necessary. I think that in general, we can try to extend this theory in many directions. Well, first, we would like to extend the general result from the dimension 2 to higher dimension, and this is already to be done. Then, of course, caloric functions or parabolic function, parabolic equations could be considered, and probably this is also for application very significant, because this very degenerate parabolic equation may have may display some strange phenomena about the diffusion of the very degenerate diffusion. So I think that it's worth working on this. There are a lot of open problems, so if anyone wants to try, is welcome. I think it's an interesting area of research.
Okay, thank you very much. I don't know if there are some other questions. So if not, I can't see any question in the chat. So if not, thank you very much for your nice talk, and we were happy to have you here. So thank you
very much.